to start with what we were doing last time. We had this funny data set that sort of had these two groups, and then we were analyzing what's the best way to do it. So this data set had an x1 and an x2, and at the end, we made up this x3 that split it right down the middle and said, we have this new feature, either you're here or there, and we used that instead. And that seemed to improve things. And then as I was leaving the classroom, I had this like really good idea. And I was like, well, if it improved things to split it in two, why don't we split it into a bunch more? So then I wrote this stuff. So I said, let's make an x4 and an x5 and an x6 and x7. We'll just like make little groups, right? And then we have more features. And then I ran the regression. So now instead of just having 2, now we've got 7. And I got this amazing R squared value of 0.9, 0.907. So I was like, this is great. We got this. And okay, some of them are not significant, but for the most part they are. So like going back to hypothesis testing, what we were doing last class. So again, you can look at the intervals and see if the interval contains 0. And the interval will contain 0 when this is less than 5%. Okay, there's one of them, x5 for some reason is 70%. But the rest of them are all under 5%. So maybe we'll throw out x7, or sorry, x5. But it's still, you know, this is a great idea. I got lots of features, try them all. This is fantastic. And today's warm-up question is, what is maybe the problem with this? So is there some kind of issue with this? You can say no issue if you think there's no issue. But think carefully about this proposal. What is the issue with just adding all these things in? And I'll give you guys a couple minutes to do that. Feel free to talk to the people near you if you are unsure. And then we'll take it up from there once you guys have a chance to do that. And the code is WPRY, which almost looks like a word. What was that? Yeah. So think of an idea and then think of a word that summarizes your idea. Yeah. And then and that's why we discussed, right? Like it's not. I don't just grade you on your 30 character word. Yeah. Okay, who's still thinking? Who needs more time? Nobody. Okay, let's view and we'll discuss based on what responses we see. So, overfitting. There's possibly overfit. It may overfitting. Okay, I like this one. R squared keeps getting higher with more examples, maybe? It could bring in annoying. New variables, not useful. Overfitted. So a lot of people are saying overfitted, which I think is what I was going for. And this is the main thing we want to talk about today. So the videos you watched were about selecting the variables. And I think it's like really good to start with, why do we have to worry about this issue at all? And it's exactly because of this. You can use as many variables as you want. You can just use more and more and like make up more. But then you start to overfit. And like fundamentally, let me draw a little graph of what we were actually doing. If I can find the actual thing where we were. So I made up these features that were different things on the x1 and the x2. Let me get my colored chalk. So we had some data, and we were kind of dividing them into little groups, right? So there's a group over here, and because I made a feature at 2.5, and I said everything from here to here, call that x, I think x4 equals 1, and fit a regression coefficient for x4. So that's like you have a new variable that is just for this little red group that doesn't see anything else that happens. And then there was another group over here from 2.5 to 5. Right, this was x5 equals 1 if you're in the green group. And then there was another one. So I'm just dividing my data into like pieces. And this was from 5 to 7, and then from 7 to 10. And this was x6 and x7. And so I've kind of just taken my data and I've divided it up into 4 groups, and then I've kind of done, so there's still regression coefficients that do everybody, but now there's another parameter that can change the value on each one. And so why is this overfitting? Why is it overfitting? Can anyone tell me, what is like fundamentally the thing that I did that is like, has an overfitting kind of flavor to it? Yeah, go ahead, it's okay to be wrong.
Well, just by splitting them into like smaller and smaller groups,
yeah,
you're only fitting just to those direct,
right,
and not to the larger.
Yes. Okay. I think this is exactly the right idea. Is where like I made an extra parameter just for the red group, and the red group has a lot less points than everybody, the entire group altogether. So if you kind of look at the ratio of the number of parameters to the number of data points, I'm making it quite bad, and I'm making it worse and worse. And so what's going to happen is, I think fundamentally the thing that you should keep your eye on is the sample size, right? The sample size. Or if you want, the sample size per parameter. So by splitting up into 4 groups, I've made the sample size in each group 4 times smaller, right? Each group is 4 times smaller than the big group. What happens when you have a small sample size? This is like the main lesson you should know about variance. When you have a small sample size, you have more variance, right? If you only have like 1 or 2 samples, then any fluctuation in those samples will throw off your entire mean. So that's what we saw kind of theoretically a few classes ago, and now it's like coming back to get us in a subtle way. So if you do this splitting up into groups, then you're picking up a lot of variance in each group maybe, and having a lot of variance is exactly what overfitting is. It's this like bias variance trade-off, and we're putting in too much variance, that's overfitting. We're fitting things too closely, so we're kind of too skewed by exactly how our sample came out. If our sample was changed, it would change what we get a lot, so that means we have a lot of bias. And so that's what's going on. So I think the thing to keep your eye on is the sample size. That is the thing, and that went down effectively, right? Of course, last class I did it once for the x2 parameter, and I was trying to argue it was okay, right? So it's not that splitting it up is always good, or is always bad. You should never split it up. Sometimes you got to split it up, sometimes you don't got to split up. What's the right answer? This is exactly what we started with in this course, which was that like weighted averaging, right? Finding the right window size. And so like you can kind of understand a lot of things in this course through that lens, right? This underfitting, overfitting is really about how do you group your data into groups so that the sample size is as large as you can, but also at the same time, maybe the red group really is different than the purple group. So I want to have my model be allowed to do different things for the red group than the purple group. So it's something you got to balance and trade off, and that's what we're going to look at today. Yeah.
You know, here we split let's say x1
Yeah.
to x4 to x7.
Yeah.
But for example, in some regression models, we see there are maybe a lot of dummy variables.
Yeah.
So actually, there are some independent variables.
Right.
So they are not, let's say, divide a variable to some specific sections.
Mhm.
So I just wanted to make sure these two cases are different. Yeah.
I think they're slightly. So I think you're talking about doing something like. So I took in my code. Let's go to my code. So I took at the variable x1 and I took ranges for it. I made x4, 5, 6, 7. I think you're talking about doing like x1 and x1 squared or something, right? Is that what you mean?
No, for example, x4 to x7 are subset of x1.
Okay, so it's true that x4 to x7 are subsets of x1, but in our model only knows about linear things, right? Because all the coefficients are linear. So I've actually done something genuinely different by allowing it to have these things, right? So before it had to say, if your x1 value is twice as big as that other guy's x1 value, the value I assign to you must be twice as big, right? Because it's linear. And now by doing this, this thing of splitting it up, I've given it a new kind of dimension of freedom. So it does genuinely do something, and it can be very good to do this sometimes, like we saw last class. But sometimes it's bad because you just like overfitting, you're just reducing your sample size. And it's the same thing if you do like x1 versus x1 squared and so on. Like that genuinely will allow the model to do things it didn't do before, and sometimes that can be good, and sometimes that can be bad.
Okay.
Yeah. So let's go back to now. Go back to your question. Say it again.
Shall I continue?
Yeah.
You know, my question, let me reword it, you know. Okay, we have got, if we have got some dummy variables in the model.
So does dummy mean that it doesn't actually affect the outcome, or does dummy just mean it depends
on
something else?
0, 1. I mean, either 0 or 1.
Ah, okay, so like a categorical.
Yeah,
sure. Okay.
But they are actually independent.
Okay.
So they are not like these, splitting a variable.
I see. Okay.
So, in this case, I assume such a thing won't be happen because I see in a lot of, I'm not sure, but I see a lot of econometrics models. They use a lot of dummy variables.
Right. So I think the answer again is it depends. So a good example would be imagine the ones and zeros, like when we have a lot of them. Imagine they don't actually affect the outcome. Like they're like noisy data that just has nothing to do with the outcome. So imagine that there's y in x1, and y just depends on x1, but then we have this like long list of categorical variables, right? That are independent, like they're not correlated anyway, they truly are independent, but they don't affect y at all. So in that case, if you put them in your regression model, it really will do exactly what I was talking about here. You're just splitting up you're just effectively just saying, okay, let's look at all the ones that are 0, 0, 0, 1, 0, 0, and like do an average for those, and then we'll do an average for these other ones. So you're just reducing your sample size effectively. On the other hand, if they really are truly independent and they have nothing to do with the model, you would hope that you would catch them by looking at the p-values, right? So if they really have nothing to do with the model, you might be able to say, oh, actually those variables that we were using, the p-values or the intervals are telling us they don't affect anything, and then you can throw them out and be happy. Whereas I guess in the example I've given, it's extra insidious because the x1 value does have something to do with y, and so these these variables that I made do have something to do with y, so you can't catch them easily. So sometimes the answer is sometimes yes, sometimes no. Sometimes it's easy to catch, sometimes it's hard to catch, but it's definitely you gotta think about it carefully. It's a very good question. Yeah. Any other questions or comments about this idea? So this is the theme today, is like, you can always make as many variables as you want. So how do you choose what variables to do? And I'm hoping to leave like a little half an hour, maybe like 20 minutes at the end of the class where we're gonna just talk about the data set you guys have for your project, which is gonna be due next Friday is the draft. And that's a housing data set. And I think you have 80 variables to work with. So someone went up to the house and they measured 80 things about the house. They wrote them down, and you have to predict the price of the house based on the 80 things. Some of them maybe are useless. Some of them are maybe very useful. If you do a regression with everything, you're going to be having exactly this issue, that you've split your data set is too small. So I think there's like 1,000 houses total. So imagine each variable is a yes or a no, right? So there's 2 to the 80 possibilities, which is some number in the like billions or trillions. So you're gonna have like one example of each type of house, and then you're gonna have sample sizes of 1. So you definitely don't want to do something like that, right? And you got to decide, how do I choose the variables I'm going to use? Maybe I want to group things together, right? These 2 variables, maybe I just group them together as one thing. It's totally up to you. There's like a million different things you could do. So that's the idea. That's the motivation. That's what we're talking about today. All right. Questions or comments? Okay, let's jump in then. The next question is, how can you watch out for this stuff? So overfitting is the thing we're worried about, which effectively is making the sample size too small. What is one way you can do it? And this was in the videos. So there were methods like the AIC, or the adjusted R squared, and the other thing they talked about was cross-validation. So the question is, which one do you like better, and why? So again, no right or wrong answer, but we're going to talk about these things. So tell me which one you think is better and why. Maybe we can list some pros and cons for these 2 different things. We'll get those on the board, and then we can start from there. Okay, we're up to 6 answers, so maybe I'll give another 1 minute, and then we'll start putting pros and cons on the board based on what you guys write. Okay, let's see what people are saying. Which one do you guys like better? Everyone likes cross-validation. Nobody likes the adjusted errors like R squared. I call those adjusted training errors because fundamentally all of these methods like AIC, BIC, adjusted R squared, they're all taking the data set that you trained on and trying to figure out how much you're overfitting or underfitting just using that, right? Which has something to do with how many parameters you used, but is difficult to tell just from the data set you used because, like overfitting is fundamentally about how you would fit something else, right? If you're fitting too closely to the training data, then you're making mistakes on unseen data. Seems like you guys all like cross-validation. Why? What are the pros of validation? All right, it tests the result. So, I mean, the other ones do that as well, but compare different models. So the nice thing about cross-validation is it works not just for linear things. I think this is one pro, is that it's very general. Very general. So it doesn't work just for linear regression, but this is what people do when they do like neural networks, which are in some sense the opposite end of the spectrum of linear regression is something like a neural network, and they still use cross-validation because it's so general, you can do it on anything. All right. Can check many groups. Independent. What does this one say? Independency-O-N-P. Someone want to tell me? Independency. Okay.
On P.
On P. Ah, okay. That's nice. Okay, good. I had to put the spaces in the right place. So what do you mean by it's independent of P?
In video says, for example, in adjusted R square and alpha E or
Right.
other ones. So P is
the number of parameters.
Yeah.
Okay.
P is in the model, but in cross-validation maybe.
Right. Okay. Yeah. This is good. So let's go to Blackboard here. Yeah. So the cross-validation, it doesn't depend on P. It doesn't depend on and P is the number of parameters. And I think this is a pro. Let me say why I think this is a pro. The number of parameters in a linear regression is kind of straightforward, like it makes sense what it is. But once you start doing something more complicated, the number of parameters gets a little sticky to measure. So for example, in a neural network, you have many parameters that are sort of redundant, right? So like you have multiple ways to express the same thing. And so do you count a parameter as a parameter, or is each of them like half a parameter, or like what? And so because of the fact this cross-validation, it doesn't depend on this number, you don't have to worry about what is a real parameter and what is not. As an even simpler thing, right? You could add suppose you were being silly and you did a regression with x1, but you accidentally put x1 on the regression list twice. So instead of having just beta 1 x1, now you have beta 1 x1 and then you have another beta 1 prime x1. Now you have two parameters, beta 1 and beta 1 prime. So somehow you've increased p, but now your model is actually doing the same thing it was before. So the number of parameters is not like, you really shouldn't think of it as like a real thing, right? Because it depends on exactly how are the parameters there. And so if you're going to use something that depends on the number of parameters, you have to be careful about what exactly is a parameter. Does it count? Does it not count? So these are very good. What else do people say? Yeah, good for small data sets and reliable. I think the thing about cross-validation, the only con I can think of, is that when you do cross-validation, you have to train your model on not your entire data set. This is really the only con, is you have to save data for testing. And then when you save data for testing, that means you, by definition, you're not using 100% of your data for training. So you're kind of like sacrificing a little bit of your data to do this cross-validation business and get all these pros. And when you sacrifice a little bit of data, that you should think of that as like, I'm sacrificing some power that I could have had, right? So I'm going to write that like this: sacrifice some data. Okay. So this is the only reason you would not want to do something like this. If you have a very small amount of data, this is actually quite bad. So like, if you don't have a lot of data to work with, and you need to pick a very simple model, and then maybe one of these is better. So the pros of these are like, you get to use all data. These have more theory behind them. So like if you want to do some actual math and like prove a theorem, you should do one of these ones for the most part. But the con is they're kind of limited. So they only work in these like specific situations. You have these like assumptions about things being Gaussian. As soon as you start doing wacky things with your parameters, like the assumptions will break and like you'll start to break these. So this is like narrow scope slash assumptions. So you should be careful when you use these. And in this course, I think I'm only going to ever do like cross-validation and stuff, just to be very general. I think this is the best. Sort of over time, a long time ago, before computers were good, this was the way to go, because you can calculate it by hand very easily. But now that computers have gotten better, and models have gotten more complicated, and people are doing crazy things with parameters, the number of parameters has grown, people don't use these as much anymore. So it's kind of like, over time, this has become more and more popular, and this has become less and less popular. The videos are a little bit old, and they're from guys who grew up when this was more popular. So I think they talk about this more than a modern video would. So yeah, cross-validation. And so the idea is exactly, I think you should think about it like this. You're going to sacrifice some of your data. Instead of using all of your data for training, you sacrifice some to use for testing. And so let's put this a little further down. So you're going to set aside some data. The data you set aside has a bunch of names. So some people call it the test set. I'll talk about why that's confusing in a little bit. Some people call it the validation set. I've also heard it called the dev or development set. So it has a bunch of names. And what it is you're taking your training data, you're splitting up a little bit aside, and you're just going to use that instead of calculating the R-squared value or something. You calculate how does your model do on this held out data set, and then you use that as a proxy for your error. Test set is a very commonly used name, but you should watch out because sometimes there is more than one test set. And so let me give you an excellent example of where is there going to be more than one test set, just so we're all on the same page. So here I'm going to the Kaggle house prices data set. This is exactly your first project. And if you go to the description, this thing comes with, and you go to data, this thing comes with 4 data sets. There's the training set, the test set, the description of the data, and the sample submission. So the sample submission is just so you know what the computer is accepting, like the format. The data description tells you what do the columns mean. So you really have 2 things, the training set and the test set. The training set is what you're going to use to do your regression or whatever, and the test set is what you're making predictions, you predict on the test set. This test set, the word test here, is not the same as the word test here. So there's like some kind of confusion. This thing is the test set, this thing is the test set. What is the difference between that test set and this test set? Yeah.
Is that test set the final test set to see how close you were to to test your model on a random?
Yeah, I think that's a good way to say it. It's the final test set. Yeah, how would you describe this one?
That test set is to perform cross validation on.
Yeah, right. So this
check your model.
This is great. Yeah. So this test set is like the final boss test set, and this is like the intermediate boss test set, right? So you train your model, and if you use the entire training data to train your model, you might overfit. And then you would do bad on the final boss test set. So what you do is you train your model on most of the training set. You play against the level 1 boss, see how you're doing, and then if you're doing good, then you go face the final boss. And that way you will kind of avoid overfitting. And the really big difference is this test set that you're given, there are no answers given. So you cannot actually test how you're doing on the test set here. All you can do is make a list of predictions, you submit it to Kaggle.com, Kaggle.com tells you what your score is, but not the answers. So this is important. It's like when if you did a quiz, right? There's a difference between getting the quiz back with which questions you got wrong, and then you like learn something, versus just getting the score. And on this final DOS test set, you never get to see the answers. You only get to see the score you got. Okay? Whereas on this, you just made this up by setting aside some of your training data. So on this like level 1 boss test set, you can do whatever you want. You can try to see what's going on, and it really is a subset of the training data. And so that's why sometimes people call this validation or dev, just to not get mixed up between these two things. And this is like, you should think of this as like the real life test, and this is like, I'm just trying to figure out what the hell I'm doing test. So watch out for that notation. That's good to know. Any other questions about that or this? So we'll have a little more time with this later, but it's a good time for questions as well. Okay. So here's a fun question you can ask. We're going to set aside some data. You're kind of sacrificing your data. How much should you put aside, right? Because if you put aside too much, then that's not good, because now you have a very small training set left to work with. If you don't put aside enough, then you can't have an accurate test, right? So that's a fun question to think about. What is the right amount to put aside? The good size is what? And it's just multiple choice. I made some multiple choice options so we could discuss. Oh, this is this test set, yeah. So the thing about the final test set is you never get to touch it. It's like, somebody gives it to you, and you're not allowed to make any choices. Whereas this one, you've actually made it up, right? You've made up your own test. So it's like you're about to go to a class to write a quiz, and like before you go, you make your own quiz to make sure that you understand the knowledge. You get to invent it, and the question is how big should you make it? Okay, I'm up to 7. Let's see if you guys have figured out the theme of the course yet. Yes, the theme of the course is the answer is always, it depends. So 10% and 20% are things like people say as a good rule of thumb to kind of like think about. So in the videos, they talk about 5-fold cross-validation, which means doing 20% of the thing at a time. I think the real answer is it depends. And it depends a lot on how your model depends on the number of data points. So if your model is very sensitive to having a lot of data, then it depends a lot, right? Because if you reduce your training set size, maybe you're sacrificing something. If your model is very robust, it doesn't care like how many points you have, or you have so much data that like taking some out really won't affect things, then you can afford a bigger test set. And the other thing you can do is, like they say in the video, is you can do this cross-validation approach. So validation is just using this idea of using a set, and cross-validation is do it multiple times, leaving out various test sets. So cross-validation. This means so the cross part means use multiple. I'm going to call them dev sets because it's the least letters. Dev sets, and average result. Okay, and the way they do it specifically, I think they talk about. You take your data and you split it into 5. 1, 2, 3, 4, 5. And then you're gonna run your thing 5 times. And how are you gonna run it 5 times? So you're gonna split your data up 5 times. And now you can see why it's good they chose 5 and not 100. So you take your data, you split it into 5, and you run it 5 times, calling which one is the dev set. You change that every time. And everything else is the training set. Training set. So here you have some train, and here you have the rest of it. Okay. So you rerun the experiment 5 times and you average the results, and that'll give you a better estimate of the error than just running it once. And so hopefully, this kind of idea is like, okay, instead of sacrificing this piece of the data sort of permanently, we'll sacrifice this piece of the data 1/5 of the time, this piece of the data 1/5 of the time, and so on. And so this can help a little bit with a better estimate. I have a little bit of a notebook here we're going to work through where we see this in action. But this is the main idea for today, using this cross-validation to try to figure out how you should train your model. Yeah.
So this is for like training your model and getting a printout of like how well it performs on a test set.
Right.
But I know you also train your hyperparameters. Is that something that occurs during this, or is this a separate cross-validation that you do?
Yeah. So this is a very good question. So in what we are talking about, the hyperparameters are the thing we're doing, and that's because if you think of a regression problem, the parameters are sort of like what are the actual coefficients, and the hyperparameters are like which variables did we select, or things like that.
Is that the only hyperparameter?
In a regression problem, I would think of that as the again, this is all like kind of in your headspace. Like there's nobody tells you what's a hyperparameter and what's not. But so you can do this. You can do this both for the parameters or the hyperparameters or anything else. So anytime you have a decision to make, or like your model is doing something, you can always do this approach. And so indeed, what we're doing it for is we're thinking of choosing what I would think of as the hyperparameters, like what variables to put in. Then the model automatically finds the parameters just by like that least squares like formula, and then we calculate the error. So our error, because the step of going from hyperparameters to parameters is automatic, it's automatic, like we've chosen like what it is, then the only thing that's left is a function of what we chose, right? And so that's what we're really testing here. In a different situation, if there was like some choice to be made in the parameters, you could do this to choose what the parameters are. So imagine, okay, this is a good example. Imagine we lived in a world where nobody invented linear algebra, right? And then to do least squares, you can't just like go bang, here's the formula, right? Which is like some miracle of linear algebra. What you have to do is try a bunch of slopes and like see which one has the lowest value, right? In that universe, they're doing cross-validation to do the least squares. Because they're like, I tried slope 1, I tried slope 2. Okay, how did it do on the held out data, right? Like, in that universe, they can do this cross-validation on that. This is like a really good. This is exactly the point of this class, right? Let's think about these like high-level things, and then on the projects you get to like nitty-gritty, put them in action. Yeah, great question. Anyone else? Okay, so in a second I'm gonna show you a notebook, and we'll go through some of these ideas. And the example I chose, I tried to pick the simplest possible example so that we could focus on this idea. And that simplest possible example is, again, it already contains this tension between big sample sizes and small sample sizes, and that's just the local averaging we did on the very first class. So that's what I'm going to show you now. And this one, maybe I'll even sit. So this is the weighted averaging we did forever ago. So just to remind you guys, we had some unknown data. And last time, okay, let me pull it up on here because it looks a little better. So we had some data in the black dots, and there was this unknown blue curve, which is secret, and we don't know. And last time I talked about how you choose the window size for your estimator. So if you choose the window size that's too big, you get a flat line. If it's too small, you're sort of like obviously overfitting. And how do you choose what is the best thing? I said, let's plot a function, which is the size of the window you chose, which is sigma or delta. So I called it delta for the nearest neighbor averaging, sigma for this like Gaussian averaging, which is like a little bit smoother, but essentially the same thing. And then I calculated the RMSE, the root mean squared error. And then I said we gotta pick the minimum, right? We want the minimum RMSE. But this was the true RMSE. So this was really, what I was plotting was the expected value of the error. So it was like y hat minus y squared. And it was the expected value over the true distribution. Right? And I could do that because, again, this is a very important thing to understand, because it's all fake, right? In the very first slide, I already knew how the data was generated. That was the only way I could calculate this graph. So now we're going to redo it again, and we're going to pretend we don't know the thing, and we're going to try to generate something that looks like, exactly the same as this. So we're going to try to generate this, but without cheating, and without using the mean function that we don't have. So again, it's the same lesson as before, but just the focus is on how do we use test data as a proxy for this guy? And it's actually not so complicated. So the first thing you can do is just ordinary validation. So how to choose it in practice using a test set. And the function I'm using, which is a very convenient function, I'll highlight here. There's a function called train test split. And what this does is it takes in your full data set and it just splits it up into a random subset for the training set and a random subset for the test set. And test in the sense of level one bus. And so all you gotta do is do train test split, x, y, and tell it the test size. Here I did 25%. And you can feed in a seed for your random number generator, so you always get the same answers if you run it multiple times. This is the simplest possible way to do it. And so what you do is your data will now look like this. So I have some black dots, that's my training set, and I have some held out green X's that are my test set. So that's one way to do it, just do it randomly. Another thing you can do is you can try to sample kind of more uniformly, right? Instead of saying pick them all randomly, maybe we'll try to get like one for each bin. And so there's more complicated things you can do, but this is the simplest. Pick them randomly. And then once you do that, now you can fit the same model, but only using the training set, right? So only using the black dots, now I can draw the curves. And again, if you make it too big, you just get a flat line. But as you increase the sigma value, you get more and more nice curves. And once you have a curve like this, you can measure how the curve is doing on the green dots on the test set. So this is like, doesn't involve the true value. This is instead an estimate, which is the sum over the test set. So this is like the true root mean squared error. And this is like the test or the development root mean squared error. And what it is just y hat I minus yi squared, and then I average over the number of things in the test set. So instead of doing the true average, I just do a sample average of the test set. And because the test set was not used to compute y hat, only the black training set was used to compute y hat, this should be somehow fair, right? Of course, there are issues that can happen. Maybe it's not fair. Maybe the X's and the blacks are actually very related in some way. So I tried to eliminate that by picking randomly, but maybe I didn't get rid of it fully. So you gotta be careful, things can happen. Maybe this is not actually the same as this. But in a nice universe, they're very similar. And then you can estimate your root mean squared error on the test set. And once you do that, so you can do a bunch of models, you can see which one is the best. And again, they're starting to overfit. But the big difference is before, when it was overfitting, it kind of looked perfect, right? You show it to like a first grader and they're like, this is a great model that goes through all the points. I did this once for a first year calculus class. And it was like multiple choice, like which model is better, this one or this one, right? And everybody voted for this one at the end. And they're like, look, it goes through all the points. That's like great. Like we just used a really high order polynomial. So before it's hard to see that, but now at least you see that you're getting a really big error on the green points. So it's like you can very easily describe why this model is bad. It does go through all the black points that we trained on, but it sucks on the green points. Those are the test points. And now once you have these numbers, you can run it for all possible sigma values. So here's just a loop. Again, doing the simplest thing, just do a for loop over everything. You can do smarter things, but I'm not doing it. And because it's quite fast, so it's okay. So again, it's nice to have a big computer. And then you get a plot like this. So the red is the test error. That's exactly what I'm talking about. The error from the test set, this guy. The green, I also plotted the true error, right? Because remember, I can cheat and look at what the real thing is. And you can see they're not exactly the same, right? And so these things are supposed to be like approximations of each other. In real life, we can never see the true error, but you can see the test error. And you can use that to choose your parameters. So here I've sort of zoomed in around where the true error has a minimum. So the true value would be like 0.25 or something. And if you use the test error, you would probably pick 0.5. So you're not going to be perfect. You're not going to get the best possible parameter, but you're going to do about as well as you can. And you can play with this and see how does it change if we change the size of the test set. So this is a good like toy model because you know everything. You can redo it. So this was for 25% held out, right? So I did a test size of 25%. Let's redo it with a larger number and see what happens, or a smaller number. Okay. So here it is again. Let's run all. So we have everything. And let me try. So 25% is a pretty big number, but not absurdly big for this held out size. Do you guys want to try a smaller one first or a bigger one and see what happens? Smaller, let's try smaller. So let's do 10%. This is like a common thing people do. So now there should be a lot less green dots. There's very few green dots. So there's only like, I think there's 100 points total. So there's only 10 green X's, right? Only 10 points that we're testing on. Okay, and you can see the model does the usual thing. And now we can plot what's going on. Okay, look at that. What happened? Let's look at this carefully. This is great. So the green is the true thing, that if we were like God, we would know what to do. The red is what we think happened, right? And according to the red, the best parameter is like 2. So it's like a very wide estimate. And not only that, because again, we know all the details about this model, the minimum possible root mean squared error is 1.0. That's like the Gaussian noise that was added on. That's this dotted blue line. Nobody can do better than this blue line. But we think we're doing a lot better. And the reason is, I think it's just because our test set was too small. Too small. Our test set was too small. We only have 10 points. And, the 10 points are random. So, just like the vagaries that we didn't get any points between 1.5 and 2, like this point maybe was an overestimate by chance. Like it's too much affecting what we're thinking, right? And it makes, when you have a small sample size like this for your test set, this is not a very good estimate of this. And so you have some problems. And again, I really think it is because 10 is too small. So you shouldn't think of 10% as being the thing that's too small. It's 10% of 100. 10 points is not a good approximation of these two things. So that wasn't good. Maybe we should do more. So let's try another one and see what happens. Let's try, where do we go? Here it is. Let's try 40%. 40%. So we saw 25 first. Let's see what happens with 40. So now we have a lot of green dots, not as many black dots. So let's see what happens. Okay, usual thing. They looking good. And then this is the fun one. We plot this and we see what happens. Okay, so now, it's not as bad. It's like the right kind of shape, not terrible. But the 25% actually looked a little better to me. The very first one we did was closer. And so to really see what's going on, let's do a really big test set. Let's do like 90% and see what happens. And this is like obviously way too big. So in real life, you would never do a test set this big because now I sacrificed so much of my training set that it's like really like a stupid thing with like 10 points that we're training on. So it's going to be quite silly. Although this red curve is actually looking pretty good. Like I'm impressed by how good it looks. Okay, now it looks dumb. Okay, see, it's just going through those 10 points in a silly way. And so probably what's going to happen is it's going to tell me that I should do a very big window. Let's see. Yeah. So now the model is really preferring and saying like, please do a really big window because I have so few training points that you need a big window for those training points to like do anything. So here we're it's not like a catastrophic error like the one I made before where the test set was too small, but it's still some kind of error where I'm preferring models that I don't want to prefer. Okay, so one way around this is this cross-validation thing. And I'll show you my favorite kind of cross-validation, which is called leave one out error. So in the videos, they talked about this 5-fold cross-validation. I'm going to show you the leave one out cross-validation. So it's also called LU. LU stands for leave one out cross-validation. And what is it? It's exactly the same picture as this, except instead of having five buckets and treating one as the set each time, you have n buckets, where n is the number of data points. And what you do is you have one special point, that is the testing point, and you use all of the rest of the data to figure out what's going on. So use n, let's say cross-validation buckets. So n is the number of data points. And I really think of it as like all the data points get together, they have a party, and they take turns being the testing point, right? N minus one of them are the training set, one single point is the testing point, and then we test everybody. Points take turns so what would that mean in our situation over here? You can imagine. So yeah, can I make if I make the test size 1%, then it'll do what I want. Okay, so here's my test set with one single point, right? So I have all the black dots and I have one single testing point. And now I can compute everything with that one testing point. Of course, this is great because I have 99 points in my training set. The model you get from these 99 points with or without this single point is going to be almost the same. So like the best thing I could possibly do is almost the same with these 99 points as with the 100. So this extra point is not affecting things much, so this is very good. The problem is, if I just use this as my test point, any errors I make over here, I just won't see at all. So what I'm going to do is I'm going to do this 100 times, changing who is the green X. And I just average the results. So this is called leave one out. The green one is the guy I left out. And if you average the results, then you get some kind of good approximation that is supposed to be better than just doing some random size for the test set. And so I have a little code over here that loops through it. This is the main reason I like Python rather than R. Writing a function like this in R I find very painful, but in Python it's not so bad. So I loop through and I make the training set like this. I just have a nice for loop. I delete one point from the training set. I add in that one single point to the test set. And then I just do exactly what I did before. And then I add up all the errors that I got and take their average. And if you do that, you get a graph that's like this. And it's a little bit biased towards bigger ones, but it's a lot closer to the true value than you would get with some fixed test size. So leave one out. It's a kind of a special case of this. If your model, maybe you don't want to do it that way. So the nice thing about the model that I'm looking at today is that the training set, if you include 99 out of 100 points, is really robust. Like it's very close to the real model. Other models don't have that property. So if you're doing linear regression and you leave out like one outlier or something, it might do something wonky. So you got to decide. But this is a way I like to do it. One disadvantage is that if you do this loop, it can be slow, right? So here I did 100 times. I had to do 100 models. But this model is so fast, it's fine. And that's why if you have a fast model, this is great. If you have a very slow model, this will take you all day. All right, so that's the leave one out error, and I kind of like that better than any single size. Yeah.
Sorry, I just want to clarify. So
yeah.
Leave one out, it goes through every single, it trains on all the points except one for
exactly.
every single point.
Exactly.
Okay.
That's right. Yeah, and that's exactly what this loop is doing. So, so the weighted average estimate function is called 100 times for every value of sigma. Yeah.
Two questions. First, in let's say previous cross-validation.
Yeah.
We didn't change the train and test sets. Yeah, we only take two and we continue with that. Am I right? Or did we change it?
So in the way I was doing it before, I was in the notebook. I had a training set and a test set, and I just left them fixed and did it once. So it was like doing 1 out of 5 of these.
Yeah.
I just did the top one.
Yeah, the question is because I see if we do loop cross-validation, something like this, with the previous cross-validation, okay, we are going to do only for one.
Yeah.
But here we have got, for example, for 25 or 20%. So maybe it is going to be closer. And the second question was about previous cross-validation. Is that if we somehow find the minimum of, let's say, minimum for each test size we choose. Yeah. And we draw it. So we may understand, for example, there's going to be a minimum or maximum in the curve, so that we understand, okay, which test size is going to be better or not. Yeah, so this is the thing I was trying to show you, is that the answer is it depends. And if you pick a test set that's either too big or too small, you can have problems. And it's kind of hard to know beforehand what it's going to be. The leave one out, if it's true that your training set is sort of very robust under this like leave one out thing, then the leave one out is a really good way to go. And so for a lot of things, like leave one out is like really like would be the best, except for the fact you have to run the model 100 times. So if you have to run the model 100 or 1,000 times or whatever, maybe it's too slow. So leave one out is very good.
this is like a compromise, right? This is like leave 20% out. I really, if you can do leave one out, you should do it. If you can do something like this is like better. But again, I think it's tricky. Like, what is the right size? I don't think there's one size fits all answer. You kind of have to like smell around a little bit and look at the graphs and see like, am I missing something? Is my test set so small that I'm missing something? That kind of question, you know. And I think it's not an easy question to answer. And later on in the course, we're going to study these methods called like bootstrapping methods, like resampling methods that kind of deal with this as well. So this is like, right now we're just letting you guys know it's a thing. We're going to get more into it later. Yeah, it's a great question. Okay. Okay, so one other notebook I wanted to show you very quickly is just doing what you guys saw in the videos. So I won't go into a lot of detail, but it is in the course GitHub. And this is, so I took the Python versions of the labs and I kind of pared down everything just to show you guys the forward selection method. So they talk about that in the course. And here is a data set on hitters. What are hitters? They're people who play baseball who hit the ball apparently. And you know, they have some data. So actually let's print out the hitters so we can see what it looks like. So it's a data set, there's some people and they have some stats, the number of times they were at bat, et cetera, and they have a salary, and we want to predict their salary based on their baseball stats. And this code, it runs through, it does a validation approach to choosing which variables to look at. So again, it's doing the same training test split. Here we did a test set of 50%, which is pretty big. But I guess the thing we were worried about is that there's only 263 people, right? So if you do a lot fewer, like if you only did 10%, you would only have 26 people in your set. So if you're gonna do it like this, you do need a chunky size, like 50% or something. So you could try leave one out instead. That might be a good idea. And then I have two functions here. One of them is process subset, which inputs a feature set and a training set and a test set. And what it does is it does the regression only using the features from feature set. And the nice thing is it does this sort of automatically and outputs the result in a nice little dictionary for us. And then I have this function called forward, and it's doing literally what you guys saw in that video of doing the forward prediction. So it starts with nothing, and then it slowly adds on one feature at a time until you have all the features. And it's always adding on whichever one is the like greedy best choice at that moment. And so what it's doing is it checks all of them and then it sees which one is the best model, and it returns which one is the best, and then we add it on. So here's a little loop where we just go through and do it. And I made it output what's going on as it is running this. Oh, I guess it's all screwed up because I'm a little zoomed in, but okay. So I made it output what it's doing, and you can see in the output how it's working. So of course you could run it without this. Because it's quite long. I just did it in the dumb way. All right. Yeah, so at first, it adds on one. Can I zoom out? Okay, here. So first it's trying one variable all the time. So it's doing the regression only using hits, only using home runs, only using runs, all the way to the 18 possible things it could do. And then it decides, it calculates the R squared for all of those. It decides that C runs, I don't know what C runs is. It decides C runs is the best one. And now it's trying C runs and at bats, C runs and hits, C runs and home runs, and so on. It decides which one is the best, and then it adds that on. It calculates the R squareds. These are the R squareds that are coming out. They're not the R squareds. They're the RSSs, the residual sum of squares, which is like some kind of constant times the R squared. And then at the end of it, you get a nice graph like this, which shows on the test set, right? Not on the training set, because of course on the training set it's always improving, but on the test set, how did the error go? And you can see there's a big drop from using 1 to 2 features. And then there's another smaller drop from using 7 to 8. And 9 was the absolute best, but then it started to get worse. And this is exactly, over here you're starting to overfit. Excuse me. And over here is kind of where you want to be. And the very last thing, I think this is an important step people forget. Now that we've decided that 8 or 9 predictors is the best, you should use the entire set to come up with that. So just using our training set, we decided 8 or 9 was the best. But now when you submit your final answer, when you fight the final boss test set, what you should do is run it again on the full set, right? And when you run it on the full set, you again we're gonna do it. We're gonna do 8 or 9, I think. Variables. So these are the 8 variables that decided to use, and it's slightly different between using the full data set and the training set. I think there's one variable that was different. I think this is a step people forget, right? So the training set test set is only to decide what is the best. Once you have decided what is the best, go back to the full data set and use that. So this is like the final answer, that if this was the project, you would run a regression with these variables, and whatever the output is, that's your answer. Yeah?
Sorry. I remember in the video, the guy said, and it seems reasonable to me, but the guy said the coefficient of each predictor,
Mm-hmm.
if we add more parameters to the model,
Yeah.
so the RSS, once we decrease,
Yeah. So this
is right, yeah.
This is, I haven't been drawing a lot of these graphs, but it's true, whenever you have one of these plots, I've always been plotting like the test error, like going back to, I think this is the easiest one to understand it. So these kind of plots, they always have this hump, right? But if you plotted just the training error, it would always go down, and it would go down to 0. So it would just look like, zoop, and it would go down to 0. And then you would be like, aha, I did it, I got 0 training error. That's not what you want. This is an important thing to remember. Yeah?
Why did we have to go through the training set to find the number of parameters and then redo it for the full set instead of doing it for the full set?
Fantastic question. So why did we have to use the training set to find the number of parameters? And I think it all goes back, again, to this graph. So this graph, what is this graph? This is the residual sum of squares, but not for the training set, for the test set, right? And the reason, again, is because if you did the residual sum of squares on the training set, it would just monotonely go down to 0. And you would just go to like, oh, more parameters is better. So the more I add, the better my model does. So the reason we have to do a training set is because we need to save some test set to make this graph. So we save some test set to make this graph, and then we can find the real minimum. Whereas if we didn't do that, we would just be like, oh, I'm a genius, like 100 parameters. That's really the reason why.
Okay.
So yeah, I think maybe I should start plotting both so you guys can see the difference. So this is the RSS on the test set. If you plotted the RSS on the training set, it would just go down, and the more you used, the lower it would be. And then if you only looked at the training set, it would seem like the more is better, but more is not better.
But then we do it for the whole set.
Yeah, so once we've decided that 8 is the best, then we can use the full data set with 8 variables. And then we submit it to Kaggle.com, and they have the final boss test set that tests how we did, right? So this is RSS on our level 1 boss test set. Yeah.
For our assignments, you used a lot of functions that you wrote yourself.
Yeah.
Would you like us to do that, or there's probably packages?
Yeah. So first of all, I definitely did use the packages.
Okay.
So I'm using like this SM package, and you should definitely feel free to find code online and use it. If you use like something and you're like literally copy pasting a lot of stuff because it's useful, just make sure you like cite it carefully. But for the most part, what I did is I just have these like simple functions. Like the main one is this one, sm.ols. OLS stands for ordinary least squares, and it's doing model.fit. That's running the least squares, and then everything around it is doing stuff like pass in a bunch of parameters. And all of this, I was also like, a lot of it is actually copied from other people's things. Like this lab is taken from those other guys who I forked on GitHub. So yeah, you should feel free to do that. And like the thing you're going to end up writing a lot on your own because you're going to have to make the graphs like this and like interpret them and things like that. So yeah, it's not a computer science course. You don't need to write everything from scratch. Yeah. So what we're looking for is some kind of like nice like document with all those parts that kind of show like what you did, and if you want, you can kind of make it like a story. Like first I tried this and it didn't work, and then I thought I'd add this on, and then at the very top you're going to put like your final model and like how it works in simple language. So the instructions are all on the website. Yeah.
And the printouts when you're going through the actual models or like the predictor selection.
Yeah.
Do you want those printouts to do you want them to be printed in the notebook or?
Yeah, everything should be in the notebook. Right. So the only thing you're going to submit is the notebook. That's the only thing that people are going to read. So for example, if I was doing this hitters data set, I would show this, and then I would say like, oh, then based on this, I chose 9 predictors, and then look, I ran the entire model on the 9 predictors, and I got this, and so I did a regression with those 9, and here's what I got. Okay, it's true, you don't want to have stuff like this in your notebook. That's like really long and like just like debugging information for you, right? So it should be kind of like nice and neat. Don't make it print out a bunch of things.
Yeah, that's what.
Okay, this is good, yeah. So I think what you should do is you can print out like a summary list, like maybe like the last line or something, right? Like I ran it, here's what it did, at the end we got this. Yeah, it should be, it's designed for a human to read as well as like to run the stuff. So try to make it readable. Great question, yeah. Okay, so in the last 15 minutes, I'm gonna like briefly go over this data set with you guys. So again, it's on Kaggle, and you have to, nobody has the test set except Kaggle. So you have to make a Kaggle account, and then you're gonna submit to Kaggle, who's gonna give you like your score on the model. Of course, your score is not just your grade, because we care about interpretability and stuff like that in your what you write. We also, for this one, we want it to be a linear regression. So there's a lot of like tutorials online where they do fancy stuff like boosting and things like that. We want a regression for this one. So show me a regression. You're not going to get the best possible score. So you're not going to win the leaderboard because you're limited by doing your regression, but that's okay. And you can submit multiple times to the final boss test set and get multiple scores and then change what you're doing based on that. So hopefully the setup is clear. And I think this is like, if you really want to be like a data scientist, having a couple of these Kaggle things on your CV is good for you. So this is why I kind of did this. So you can get practice with this. If you like it, you can do other data sets, you know, during the course or after or whatever. Let's look at the data. So the data has 80 columns. There's the sale price, that's what you're trying to predict. Well, I will say, let me tell you one important thing about the sale price. And I think where is it written? There's somewhere very sneaky. Is it under overview? Rules? Oh, overview evaluation. Okay, cool. It's your job to predict the sale price for each house. Metric. This is how we're grading you, right? Or how the Kaggle grades you. Submissions are evaluated on the RMSE, the root mean squared error. Okay, that's good. Between the logarithm of the predicted value and the logarithm of the observed sales price. So this is good to know. You're not trying to predict the actual value of the house, right, in dollars. You're trying to predict the log of the house. So when you do your regression already minimizes root mean squared error, but make sure you're doing the regression with the log of the house value, not the value directly. And you know, they have in brackets, taking logs means that errors in predicting expensive houses and cheap houses will affect the result equally. So this is good to know. If you predict the price of the house and not the log of the house, you're gonna do artificially bad on this because you're optimizing the wrong criteria. So that's a really important one to know. And yeah, this is what your submission is gonna look like. It's gonna have 2 columns, ID and the predicted sales price, and you're just gonna predict the house price for everything in this data set they gave you. Yeah.
So when we get our data set, we should automatically convert that sale price to logs.
You should convert it to logs, predict the logs, and then you gotta convert it back to dollars to put here. Okay. And then this is a really good tip to know. And if you want to dig in, while we're talking about this, if you dig into the data, so here's a notebook where somebody has some analysis of the data for you. So feel free to read lots of things like this. If you plot the actual price, it looks like this, which is not quite normal. But if you plot the log of the price, it looks more normal. So let me see. I think they do that later on. Okay, yeah. So here's the sale prices, and here's the best Gaussian fit to the sale prices. It doesn't fit very well. But if you take the log of the house, the log of the price, it looks like that. So the log of the house price looks like that, and it fits a Gaussian much better. So a lot of things in real life, they're not Gaussianly distributed, they're log Gaussian, or log, people call it log normal. And that happens when things are sort of a product of many independent things that will tend to be log normal. So you gotta make sure you do the log of the house price. And again, you should feel free to read, like if you go to Kaggle, another nice thing about Kaggle is there's a lot of tutorials and stuff. So if you click on tutorials, it'll have some stuff about this data set. So if you want to use R, there's some R ones. I've done everything in Python. The videos are in R. If you want to use R, go ahead. You're still going to submit the same thing. You're just going to change the setting on your notebook to say run R code instead of Python code. So if you want to use some of those, go ahead. Here's some Python ones. I will say some of these are not applicable. So for example, this one is all about XGBoost. So XGBoost does something called gradient boosting, which is like a way to fit models really well, but not understand what they're doing. So you kind of lose the interpretability and you get good results. So we don't want to do that because we're doing linear regression. Although it does say it includes linear regression, so maybe, I don't know, maybe there's something helpful in that. But feel free to read these. Obviously, don't copy them exactly. Cite when you're using them and like when you're inspired by them. But you gotta write your own thing at the end of the day. So going back to the actual data, I will say the main thing you're gonna have to be doing is just sifting through these columns of that you're given. So there's so many different things here. And some of them are numbers. So like, let me think. Okay, actually, I think there's a better description down here, yeah. So some of them are categorical, right? Like, is it a 1-story house? Is it a 2-story house? But a lot of them are numbers. So a good example of some important numbers. Overall quality. So somebody rated the house from 1 to 10. That's an important number. The condition, 1 to 10. I think there's like the square feet of the lot, the square feet of the house, excellent, good, average, fair, poor for the quality, stuff like that. So there's a lot of numbers, but there's also a lot of categorical ones. And you're going to have to decide like how to include those, which ones to include. And you're going to do it sort of through some cross-validation approach. Yeah?
Sorry. You know, a couple of minutes ago, you showed the way you should submit the result.
Right.
So I understand there's going to be a table with 2 columns.
Right.
The first one is the index, and the second one is going to be the coefficients of the predictors.
No, that's wrong. You don't submit the coefficients of the predictors to Kaggle. You only submit your final number. So you submit what you think the house costs. So it's on your actual submission to me, that you're going to have some interpretation where you're going to look at the coefficients and say like, oh, this coefficient is positive, that means this. This coefficient is negative, that means that. And like kind of interpret what's going on, what your model did, and like, is it reasonable? But for Kaggle, they only want your raw numbers.
Okay, but the estimation is on the whole data set,
Yeah,
right?
that's right.
Okay.
So you're going to use your entire training set to make the estimates, and then you're going to apply the estimates to this test.csv, which is the final boss testing set. Yeah. Okay, so that's essentially what you got to do. The draft is due next Friday, and then we're going to have a week where you guys read each other's drafts and like give feedback to each other, and then you're going to have another week to do your final submission. So you're going to have like 2 weeks between draft and final. The draft, I'm not going to give it like a detailed grade. It's going to be like a completion grade. Like, did you try? Did you do like 1 submission on Kaggle? If you do that, you'll get full marks for the draft submission, and then like 99% of the grade will be the final submission. If there's any other questions or comments, feel free to post on Campus Wire. I'm happy to clarify. And you guys can talk to each other and work together, coming up with ideas. You do have to write your own at the end of the day. I don't know. What else should I say? Let me leave it for questions. Okay. So let's finish 5 minutes early then. I'll be here. If you have questions, feel free to come by or to office hours or post online.